Okay, in this example, we're told we have 1 kilogram of water contained in a piston cylinder assembly. So let's go ahead and sketch that out. Here's our cylinder, here's our piston, and we have our water in here. This is going to be our system that we're interested in. And we're told that it's initially at 160 degrees C, and the pressure is initially 150 kilopascals absolute. It undergoes an isothermal compression process to saturated liquid. So state 2 is going to be, state 2 is a saturated liquid. And it's isothermal, so T2 is 160 degrees C as well. For the process, the work done by the water is minus 471.5 kilojoules. So I'll just draw it this way. This is the work done by the system, and that's the minus 471.5 kilojoules. And then determine for the process the heat transfer into the water, so that's our heat transfer in, and the change in entropy of the water. Okay, so to find the work done by the water, since we're given, to find the heat transfer into the water, we're given the work done by the water right here, and we're trying to find the heat transfer. So this makes me think of using the first law of thermodynamics on that system. Since I'm given some information about the initial and final states, I should be able to find the change in internal energy, and then I can connect it all together using the first law. So let's write that out. So the first law, the change in total energy of the system is equal to the heat going in minus the work done by the system. The change in total energy is going to be the change in internal energy plus the change in kinetic energy plus the change in potential energy of our system. We're going to assume that the change in kinetic and potential energies are negligible. So assume negligible. The pistons, I've drawn it here being horizontal, so there wouldn't be a change in potential energy, and we're assuming it's moving quasi-statically, so the velocities aren't appreciable either. So let me go ahead and rearrange this to solve for the heat transfer in. So that's going to be delta U plus W by. Well, the W by we were given, that's minus 471.5. Notice that it's negative, which means that work is actually being done on the water rather than being done by the water. Now the change in internal energy is going to be the mass of the water times the specific internal energy at the end minus the specific internal energy at the beginning. The mass of the water we're given as being 1 kilogram. Now to find the specific internal energy after and before, we can make use of the information we're given about the states. So at state 1 we're given the temperature and pressure. We can use the property tables for water. And when we do that, we'll get that U2. And by the way, I use the property tables coming from the Moran and Shapiro textbook, 7th edition. This one came out to be 95.2 kilojoules per kilogram. And it's a superheated vapor. And then state 1, which we're told is a saturated liquid, I get to be, I messed this up. State 1 is the superheated vapor. Apologize for that. And state 2 is the saturated liquid. That's 674.86 kilojoules per kilogram. So saturated liquid. And again, I got these values out of the property tables given in the Moran textbook. Okay, so now that I have all this information, I have my mass, I have my specific internal energies before and after, I have the work, I can solve for the heat transfer. And if you do that, you'll get the heat transfer in is minus 2390 kilojoules, should be kilojoules. And should be kilojoules there. And that means that there's in fact heat transfer out of the water rather than into it since it's negative. Okay, let's go ahead and work on the second part, the change in entropy of the water. This one's pretty straightforward. The change in entropy will just simply be change in entropy. That'll be the mass times the change in specific entropies. Again, we know the mass is 1 kilogram. And we can look up the values for the specific entropies, so we can use the property tables for that. And again, I use the property tables out of the Moran and Shapiro textbooks. So what I get for S1 is 7.4665 kilojoules per kilogram Kelvin. And for S2, I get 1.9427 kilojoules per kilogram Kelvin. Again, if you're using different tables, you may get different numbers, but out of the Moran textbook, this is what I get. So when you plug this in, you can get the change in the entropy, which comes out to be minus 5.5238 kilojoules per Kelvin. So the entropy is in fact decreasing in this process, which is fine. You can have a decrease in entropy. The reason it's decreasing is because the heat transfer is actually going out of our water. It's not going in. What can't be negative is the entropy generation. The change in entropy can be negative, but entropy generation can't be negative. And in fact, it's not uncommon to have the change in entropy be negative as long as there's heat transfer going out of the control volume. Now, we weren't asked to do this, I don't think. Let's see. Yeah, we weren't asked to do it, but we'll sketch out the process on a TS diagram. These are pretty useful, just like PV and TV diagrams. TS diagrams are also pretty useful. So here's our vapor dome, and let me draw in our isotherm here. I'm sorry, an isobar. So this is our initial state. We were in a superheated vapor initially, so here's our state 1, and this is the 1.5 bar isobar that's corresponding to this pressure of 150 kilopascals. And then it's an isothermal process, so we're moving along at the same temperature. This temperature is 160 degrees C, and state 2 was a saturated liquid, so that puts us right here. So our path heads that way. And you can see here is our S2, here's our S1, and you can see that the change in specific entropy is negative, right? Our S2 and S1 values are right here. So S1 is larger than S2. So that's what it looks like on a TS diagram. I didn't show it here, but you can also draw the other isobar, and I don't know what that pressure is. I didn't look it up. But anyway, you can put that in there as well. Another thing we weren't asked to find, but I'm going to do it anyway, is to look at the entropy generation. So for that, I'm going to use the entropy equation. So we weren't asked to do this, but it's, let's go ahead and do it. And we're going to do this to find what the entropy generation is in this process. So let me write out the entropy equation here. So here's our entropy equation for this particular system. So we have the change in entropy here. Here's our entropy generation and going from state 1 to state 2. Here's the heat transfer into our system divided by the absolute temperature where that heat transfer occurs. And this is going from state 1 to state 2 along the boundary. So in our particular case, we'll go ahead. We're told that it's an isothermal process, and we know what the heat transfer is. We found the heat transfer up here. We know everything's isothermal. So, and we also know delta S. So we have delta S here. It's the S2 minus S1 is the minus 5.5238 kilojoules per Kelvin. We know the heat transfer. That's going to be the minus 2390 kilojoules. And the temperature was 160 degrees C, so we need to convert that over to Kelvin. So add in the 273 Kelvin there. And then we can solve for the entropy generation. And when you do that, it comes out to be 4.5 times 10 to the minus 4 kilojoules per Kelvin. So that number is pretty small. I would say that that's pretty close to 0. It's not exactly 0, but it's pretty close. So this process is close to being internally reversible. Since the entropy generation is so small, nearly 0, I would say it's internally reversible, this particular process. If this number was negative, then we know that the process is impossible. You couldn't have it. And if the entropy generation is a really large number, then that means there's a lot of irreversibility in the process. But since it's pretty close to 0, I'd say it's nearly reversible. Okay, with that, we'll go ahead and end the exam.